Well, we're almost done, aren't we? Well, we've talked about congruence transformations, but we haven't talked about similarity transformations. We've talked about isometries and how one figure is congruent to another if a sequence of isometries maps the one onto the other. What we haven't talked about yet is what do you do with these figures? We know that they're similar, but there's no way to get isometries to map the one onto the other. We can get through an isometry, we can bring this one over to here and kind of turn it like so, so that it sort of matches up, kind of, but we can't get the one to map onto the other, obviously. So what do? Well, we bring in our friend the dilation. In a dilation, you have a center and a constant of proportionality. So some fixed point O and some constant of proportionality R. And that's defined in such a way that if the image of A is A prime and the image of B is B prime, then the distance between A prime and B prime is R times the distance from A to B. In a dilation, the center O is a fixed point. It does not move. Every other point moves, and the image is R times as far from O as the original point is from O. So if we're talking Common Core transformations, what happens in this case? We've got triangle A, B, C, triangle D, E, F. How do I know if one is similar to the other? Well, through a sequence of transformations, let's clone this thing. I slide this over here like so, so that angle B matches up with angle E. Angle B matches up with angle E. E is B prime. This is A prime. This is C prime. There is an isometry that will make that happen. This angle congruent to this angle. Now, when we talked about similarity, we talked about side angle side similarity, because what ends up happening here? The ratio of AB to BC is the ratio of ED to EF. And so by the parallel projection theorem, these guys are parallel. So if I were to dilate with a center at E and a ratio of ED to BA, then this dilation would turn this triangle into this triangle. So the side angle side thing is a big deal, side angle side similarity, because if we have that, then this sequence of transformations will do the job. It's not the only sequence of transformations that will do the job. In fact, once we dilate by this factor, regardless of what the center is, there will be an isometry that will map the one onto the other. And so we say that two figures are similar if there is a similarity transformation that maps the one onto the other. A similarity transformation, a dilation plus an isometry or sequence of isometries. Okay, it doesn't just work for triangles, it works for rectangles also, works for a whole bunch of figures. So, let's clone it. Let's clone it. So I bring this figure over here so that this vertex maps to that vertex, and then I dilate, and I can dilate if the ratio of, let's see, this is RECT, and this is the image. So if I'm going to dilate, this is E prime, this is C prime, this is T prime, I have to know that IM to RE is the same as IG to RT. If that's true, then the dilation centered at I with factor that is going to get this job done. And map this rectangle onto that rectangle. Doesn't just work for polygons. We could talk about circles. How do I know that circles are similar? Well, we know that this has some radius, maybe little r, and this has some radius, maybe big R. So the first thing we do is we perform an isometry that sends the center of the one circle to the center of the other. It maps, let's call it O to O prime. And then what? Well, then we dilate. We dilate centered at O prime. What's the, ooh, that's ugly. We dilate, center at O prime, and what's the scale factor? Well, the scale factor is big R over little r. And if we can do that, once we slide the circle into position, the dilation finishes the job. Together, that isometry and then dilation is called a similarity transformation. And two figures are similar if a similarity transformation takes the one onto the other. It's not just that a dilation takes the one onto the other, it's that an isometry and a dilation, the composition of the two, take you from the one onto the other. And similarity transformations do all the things you think they're going to do. They keep collinear points collinear, they keep segments, segments, and lines, lines, and triangles, triangles, and circles, circles. They do all the things you expect them to do because a dilation is just to stretch in all possible directions. Okay? Okay. So that's the thing you need to know about dilations and their connection to similarity. Two figures are similar if a similarity transform can be found, a combination, a composition of an isometry and a dilation takes the one onto the other. Okay, so that's your big idea. There it is. Off we go.